Hello friends, and welcome to the last lecture of simulation of ethyl benzene process. In this lecture, we will simulate the final distillation column, and this distillation column is the product distillation column. And the bottoms of the product distillation column is nothing but the diethyl benzene, which is recycled. So without delay, let's start. Now let's have a look at the flow sheet first, that is in the published article. Now in the flow sheet, what we find is, yes, column C2. We have already simulated this column. Now we need to simulate this column. Column C2 operates at a pressure of 0.1 atmospheres and it has 24 trays. Okay. So with this information, let's proceed with the simulation. The bottoms of column 1 are fed to column 2. So let's draw another ChemSep unit. So after selecting the ChemSep unit, we can place it on the flow sheet and let's give this a name. So I give this the name as Ethyl Benzene Column. Now next we configure it. So double click on it, click edit. And since it has 25 stages, we include now remember one thing, that whenever we write the number of stages, we have to include the stages are counted in this software as the condenser and the reboiler also. So we have to take 26 stages, right? So 24 was shown in the flow sheet plus 2, one for the condenser, one for the reboiler. And we adjust the pressure to 0.1 atmosphere. That is the column pressure. And click enter. Click OK. Now we have got the ChemSep interface. Let's close it. Click yes. Now let's attach the top stream of the distillation column and the bottom stream of the distillation column. So this gives a 25, so double click. Now adjust it to 25. Yes. And the feed stream as given in the article is at the 15th stage. So let's put that. And as I had discussed in the previous lecture, we have to give tolerances which are less to start with so as to converge the distillation column. So let's keep the top tolerance as component recovery as 0.99 ethyl benzene and the bottom component recovery as orthodiethyl benzene, and this we take it as 0.9. This will allow us to converge the column quickly. So let's simulate the column now. So what we can do is, instead of simulating this entire flow sheet, we can right click on the column and click calculate this unit. So it will do the calculation only for this unit instead of simulating the entire flow sheet, which will take a longer time. So we are finished with the simulation, and what do we find? We find that on the top you have a good amount of diethyl benzene slipping up, and you have lesser amount of ethyl benzene than what we desire. But nevertheless, the column has converged. So what do we do now? Now we increase the tolerances slowly. So we put it as 0.999 and we put this as 0.99. And we again resimulate it. It's done. Now let's have a look at the results. So we are very close, that is 629 and 2.822. So what we can do is now further increase the tolerances and have a look at what are the results we get. So let's go to column specs once again and let's give a 4-digit recovery and let's give here a 3-digit recovery. And let's recalculate this. As we see, the simulation does not run. So, yes, it does not run. So we edit it once again and we get back to our original specifications that we had given. In this case, it was 3 decimal recovery and 2 decimal recovery at the bottom. So let's keep 3 decimal recovery at the top and 3 decimal recovery at the bottom, and let's see whether the column converges. So let's do it once again. No, it does not. So let's go to our original specification and converge it first. So it has converged. Now to improve these results, we can use another trick up our sleeve, which is give the flow rates. Now instead of component recovery, what we give is component flow and the component flow of ethyl benzene. Now we know that the component flow of ethyl benzene is 630.59 kilomole per hour. So we enter this, and the component flow of diethyl benzene, we fix it to 281.9, which is very close to 282. Enter that and let's see if the column converges. And yes, indeed, it has converged. Now let us see what is the top flow rate. The top flow rate is 630.5904 and the bottom flow rate has 281.90016. Now we can further improve on the results. So we go to edit and we go to column specifications and we put it as 281.99, which is fairly close to 282. Enter it and simulate this column. Well, it did not simulate. So we go to edit. And we put the original value of 281.9. And this time we take a slightly more flow, kmol per hour, 281.92. And let's resimulate it. It does not simulate. Therefore, our best option in this case is to take the bottom flow as 281.9 kmol per hour. And simulate it. As you see, the simulation has converged. Now we run the entire simulation. So we adjust the column and we run the entire simulation. We adjust the look and let's run the entire simulation. And there we are. It would indeed converge. Now, what do we have? On the top, we have 630.59, which is very close to 630.6. And on the bottom, we have 281.9, which is very close to 282, which is nothing but the recycle DEB. Now comes the final step, that is hooking up stream number 22 to recycle DEB. Again, I would like to warn most of you that you would take stream number 22 or take recycle DEB and connect it off to the bottom of the distillation column. This would lead to a lot of error because once again, remember the recycled DEB enters the reactor at 20 atmospheres, but the bottom is coming at 0.1 atmospheres. We have to connect this stream through a pump and then recycle it back. But most of you skip it and then we don't realize what mistake we are doing. So let's go ahead, take a pump, put it up here. Okay, so now I'll do a bit of renaming. I will rename this as pump number 1 and I will rename this as pump number 2. And now take stream number 22 and connect it to pump number 2. Now double click on pump number 2 to configure it. So click on edit, select outlet pressure, and the outlet pressure now is 20 atmospheres. Now draw the outlet stream of the pump and there we are ready. Right. Now let's save this simulation. Because we have come thus far, remember, while recycling, it may happen that the flow sheet might crash. So let's make a copy of it. So file, save as, flowsheet 1.3. Now go to flowsheet, go to configure and go to flowsheet options and we take the relative tolerance as 0.1. Now remove stream number 23 and take the recycle DEB stream and connect it to the pump discharge. Simulate the flow sheet. It has converged. What do we find? The recycle flow rate is 281.9 and the flow rate out is 630.59 and we have a complete flow sheet now. This flow sheet has been simulated. In is equal to out. Now, what is the advantage? Now, one would ask, all the students or all the professionals who would be looking at this video would ask, what is the fun in simulating it? We could have done an energy and mass balance on the paper and itself got it done. Remember, the information that we have got here is what is the number of trays you are going to have in the distillation column. The energy required in the distillation column now is available to you. So if you click on edit, And if you click on mass and energy balances, you get all the report of what is the energy requirements of the distillation column and what are the various menus in this distillation software. I have discussed it in another video, and you can have a look about that in the playlist. Most important, we have got the loads, heat loads of the reactor. Now in this case, the heat load for the first reactor is 10,791 kilowatts, and that in the second reactor is 773.19 kilowatts. Now let's have a look. Let's go to the article. Okay, so we have 10.3 megawatts. We are fairly close to the simulated results. Yes. So let's click it to megawatts. It is 10.791 or 10.8 megawatts. The error is less than a percent. Please remember, we have come close to 1% error in estimation of the reactor load. Now the second reactor load is 0.773 megawatts, and let's see what do we have in the article. In the article, we have the load of the second reactor as 10 point. No, it's not written. So fine, it's not written, but we have estimated it off. And there we are. Now, if we want a stream report, okay, that what are the flows in the various streams, all you have to do is go to Flowsheet, and after go to insert, and then afterwards go to stream report, click it and select all the streams, because we would like to have a report of all the streams, and click OK. Now at the bottom you will get a stream report which will show what is the flow rate and the concentration in each and every stream, and what are the temperatures and pressures. Now this gives a very clear overview of your process. This is a full simulation. A lot of things can be done in this. We can change the number of trays, we can change the feed conditions, and we can have a look into what is going to be the effect in our flow sheet. How much is the load going to change? How are the number of trays going to change? Well, I leave that exercise to you. People who would like to do that exercise and come up with some exciting results, or do come up with some exciting results, write it in the comment box. If you want me to make another video on how we can change the flow rates and re-simulate the problem, well, I'll make a video on it, but this will be on request. Right? A simulation of this kind can be used in the bachelor's project, bachelor's final home paper. Such a simulation can be shown. And this is a work which is equivalent to a bachelor's report in most of the universities, the final project report. So hope you have learned, not hope, but I am very sure now that you have learned how to simulate an entire process. If you have stuck till this video, you have just ended the exciting journey, and you have opened yourself to a new area of process simulation, which is one of the leading fields today in chemical engineering, which has some of the highest paying jobs too. Do like and subscribe my channel. This is very important to me. My subscriber base as of now has not touched 1,000. And to sustain such kind of intellectual work, I do need 1,000 subscribers and more. Do view my videos, a lot of them, a lot of times, so that I get a lot of sufficient number of views too. And when you view it, when you share it, and when people view it, then the Google algorithm or the YouTube algorithm ensures that this video is available whenever it is being searched, or it is at least it goes as a search promotion. So that way, many people, the more the number of people view it, more is the number of people who are going to get it. Fine, that would be all. Have a great day. Enjoy. Great days for chemical engineering are ahead. And yes, share my videos, subscribe, like them, share it to people who would be interested, and ask them to subscribe it. Goodbye. Have a great day.